So first of all, thank you so much for inviting me among these great researchers. I'll do my best in honoring infants' capacities. So with the description of the snark effect and all the related work in the interaction between number and space, a line of research has begun, which is interested in the origins and the developmental course of numerical representations, and in particular between the link between number and space. And more generally, I think that infant studies are very informative for the ontogenetic and evolutionary processes in establishing the functional link, more general terms, between space, number, and time. Okay, so this is a very simple depiction of the mental number line, in which numbers are conceived as magnitudes representing a continuum which is spatially oriented. And I think that under this mental line model, this model enclosures the general phenomenon of an interaction between number and space. And I think this interaction between number and space could take two forms. On the one hand, we can think of numbers as being associated to different spatial extents, depending on the number magnitude. So the larger the number, the larger the extent associated to it. And on the other hand, as the snark effect shows, numbers could be associated to different spatial positions according to their magnitude and or their numerical order in the sequence. So here I'm depicting a left to right orientation, but we know that there are other types of orientations. So this dichotomy could be a basis for the evidence that I'm going to show from the infant literature. And I'm going to show you that infants around 8 and 9 months of age are able to link representations of number and representations of length. They are also able to link temporal duration and spatial extent, and they are able to link these three dimensions also bidirectionally. And finally, I will show you some very recent data that we are very excited about newborn infants and how they behave when they have to link these three dimensions. And for the other type of number-space interaction, I will show you also a recent study in which we tested 7-month-olds in their abilities to map numerosities to different spatial positions. So I will start with the first part. In this first experiment, we investigated the ability of 8-month-olds to link the representations of number and space. This study uses an habituation reaction to novelty method. So infants are first habituated to a series of increasing numbers that are either doubling or halving. So here's the example of what an infant will see when they are seeing an increasing sequence of numbers. They see photos, then 8, 16, 32, 64. And they are habituated to this sequence again and again with different figures and colors, but there is always the same numerosity, which is doubling in number. Another group of infants will be habituated to the exact same numerosity arrays, but this time it will be in a decreasing order. And we measure the looking times to these displays. So here you see the mean looking times in seconds, and here are plotted the habituation trials, and you see how the looking time decreases across the trials. But the last 3 habituation trials, the looking time has significantly decreased relative to the first 3 trials. And this is the moment that signals that the infant has habituated to this information, at which point we show the test trials. So it will consist of new and familiar information. In this particular experiment, instead of presenting again numbers, we presented line lengths that either double or half in length. So this is the sample of length doubling, okay? And all groups of infants, so both groups of infants, will receive both decreasing and increasing length in alternating trials, and we will measure their looking times during these 6 test trials. And what we see is that the effect of habituation is generalized to the familiar order, this is the familiar order, but that there is a significant recovery of attention when the infant observes the novel order in the length dimension. So, for instance, if the infant was habituated to increase in number, now they look significantly longer to decrease in length. So this is evidence that infants could transfer the discrimination from the numerical domain to the spatial domain or to a dimension of spatial extent. Next experiment I want to show to you, this was by Mahesh Srinivasan and Susan Carey, and it was at the same time that we were studying this number length mapping, but they were interested in temporal and spatial mappings because they were investigating the origins of linguistic metaphors, that is, that we tend to use spatial language to refer to temporal dimensions, and they were investigating this issue. And they presented a series, these are 9-month-olds, they presented a series of congruent pairings to children, to infants. So here, a very short caterpillar is paired with a small temporal duration and is accompanied by a sound in order to underlie the temporal dimension. And with the caterpillar growing in length, also the time will grow in length. So they show again and again these pairings in which spatial extent and temporal duration are congruent. The shortest in one dimension will be paired with the shortest in another dimension, and so forth. When infants are habituated to these pairings, they were shown in the test trials familiar pairings, so the extreme values. Here's the shortest caterpillar paired with the shortest sound and temporal duration, and the longest caterpillar paired with the longest temporal duration and sound, together with new pairings. And the new pairings consisted of the same information, but they were incongruently paired. So now the longest caterpillar is paired with the shortest duration, and the shortest caterpillar is paired with the longest duration. And they observed the looking times, as I explained to you before. And what they found is that infants in this condition, they look significantly longer to these pairings than to the familiar ones, suggesting that they were able to extract the rule in the congruent pairings, apply to the new examples, and detect that those pairings are not adjusted to the rule that they learned. In a second condition, what they did is exactly the same, but in a mirror. So they habituated infants with incongruent pairings. So here the longest caterpillar will be paired with the shorter time, and so forth, until the shortest caterpillar is paired with the longest time. So they have the same exposure to this information as they had before, but now the pairings are inversed. The shortest in one dimension is paired with the longest in the other dimension. In test, as in the other condition, they show the extreme values, which are familiar, together with new values, and in this condition, the new values are represented by congruent pairings of the same values, but paired in a congruent way. So shortest with shortest and longest with longest. And what they found is that here infants don't look significantly longer to any of the two pairings, suggesting that here they couldn't extract the rule and apply it to new exemplars. So with this study, Srinivasan and Carey showed that 9-month-old infants learn and productively use mappings between spatial extent and temporal duration, provided that these two dimensions are paired congruently. This is the third study I would like to show you, and this is again with 9-month-olds. And in this study, the authors investigated the links that infants are able to make between the three dimensions, space, time, and number. I will show you just one example, because it's kind of complicated, but what they do is they habituate infants to a rule in which they pair some features to, for example, here the length or the size. So here the smallest size or length is represented by elements that are white and with black dots, and the long length or large extent is represented by elements which are black and with white stripes. And they show various instances of this rule. For example, here again, this is the longest area, and this is the smallest, again and again, until the infants are habituated. And in test, they show them the same features, but in another dimension. In this condition is number. So this would be an incongruent pairing because here there are 5 elements and here there are 10, and the smallest number has the features that before they had learned that it was associated to the longer spatial extent, while here the congruent rule, the smaller and the larger number follow the rule that was shown for the spatial extent. They show that the infants can do this. So at test, they show an increasing significantly longer looking time to the incongruent trial, suggesting that they were able to extract the rule and transfer it to another domain. And they did this across the dimensions of space and number, space and time, number and time, bidirectionally. So it didn't matter from which dimension you have to transfer. So this is a very nice article showing that there is a bidirectional transfer between the dimensions of space, number, and time in 9-month-old infants. Okay, so although these studies that I've shown to you are relatively recent, the observation of these interactions in development is not that recent. So, for example, Piaget already observed how the information of number and spatial extent and temporal duration and space is confused in children. And, for example, in his famous number conservation task, it's a very nice example for seeing how children, aged from 3 to 6 years old, I think, when the experimenter presents 2 rows of tokens aligned perfectly so that there is one-to-one correspondence, they agree with the experimenter that the 2 rows contain the same number of tokens. Now the experimenter in front of the kid spreads one of the lines, and now the kid is confused and thinks that not only the length of this row changes, but also the numerosity, that now this row should contain more elements. So this is observed by Piaget a long time ago, and it shows nicely how these dimensions were interfering with each other. But instead of seeing while Piaget saw it as a way of showing that numerical representation was immature in these kids, more recent researchers, they see it as evidence that there might be a unique system of magnitude that is dealing with all these dimensions and that represent these dimensions under a common code or currency, and that this would explain why we observe all these interactions. And I think these data are also very nice from infants, and they are relatively recent also. And they show that there is a similar developmental trend in the ability to discriminate instances in the dimensions of time, area, and number, so that at 6 months of age, infants need a 1-to-2 ratio to discriminate across the 3 dimensions, but at 9 months of age, infants across, again, the 3 dimensions are able to discriminate it with just a 2-to-3 ratio. So suggesting again that there might be a common mechanism that deals with the comparisons of these dimensions, or at least that these different mechanisms have the same constraints in processing. But what I'm interested in is where are the origins of this number and space interaction, and now we are also introducing time as another dimension, a relevant dimension. And it could be that these studies that I showed to you, which are testing 8 and 9-month-olds, that they learn these mappings because they are exposed to the natural correlations that occur in the environment. For example, it will take more time for me to drink more milk, and more milk occupies more space. So this is a natural observation. They have had a few months to learn this. But it could be that these mappings are given by an early predisposition to relate these 3 dimensions. And I think that newborn studies can offer an answer to distinguish between these 2 possibilities, because they didn't have much time to learn these natural co-occurrences. So this is what I showed to you now, some studies with newborns, which are aged from 0 to 3 days. And I will go through the method first in detail, because then the following experiments use the same method. So first we we familiarize newborns during 60 seconds with a sequence of sounds. In this example, there are 6 sounds, together with a short line. And I will show you a movie to just so you see how it looks like.
Yo. Do. Na.
Okay, I heard this many times. So newborns are seated and are hearing and viewing this information for 60 seconds. At that moment, we change the number, so we present them 18 sounds, so the 1 to 3 ratio, because Veronique and Arlette Estrella have shown that that's the ratio that newborns need to discriminate between numerosities. And this new number will be paired either congruently, so with a long line, which is the triple of the short one, or with a short line, which will be an incongruent pairing. I will show you what a congruent test trial looks like. There are 18 sounds. Okay, this is an incongruent trial. Doesn't work, eh? Okay. So one group of infants receive 6 in habituation, then 18 at test. Another group of infants receive 18 sounds, always paired congruently, so paired with a long line. And then at test, we change the number, 6 sounds, pair both congruently or incongruently. And we find that here is plotted the looking time in seconds, that newborns prefer to look to the congruent mapping relative to the incongruent one. But there could be a confounding here, and it's the following. Imagine that the newborn just look at the line. He didn't care about the number, or at least he didn't establish the mapping between the numerical information and the spatial information. So he saw this line for 60 seconds, and then he sees a new line. Oh, I like that one because it's new. So that would be enough to succeed in this task, because this will mean that she looks to the congruent, and the same thing here. So we ran a control to address this problem. And what we did now is we familiarized on incongruent mapping. So now the short line is paired with 18 sounds, and at test, we change the numerosity, and we pair them again with the 2 lines. So note here that if the newborn is just paying attention to the length of the line and is not caring about the numerical information or the congruency between the 2 dimensions, he might look just at the long line, which will be represented by the incongruent mapping. It's clear. And we showed that, we found that actually newborns don't prefer to look to anything. These looking times are similar to the incongruent mapping in the congruent familiarization condition, but are both significantly different from the congruent mapping in the congruent familiarization. So newborns were taking care of the congruency between the 2 dimensions. And this is a small graph just to show you that the time they spent looking to the familiarization was equivalent for the 2 conditions. So it's not that a group of infants, of newborns, have more opportunities to learn the information. So in this experiment, in this condition that I've shown to you, newborns could have mapped number or time, or both, to a spatial extent, because the sequence of 6 sounds was shorter in time than the sequence of 18 sounds, 1/3 of the sequence of 18 sounds. So we run another condition in which now we control for the temporal dimension, so that the only available information now is number, sorry. And I will show you, so the 18 sounds are exactly the same. I just will show you how it looks like now the 6 sound sequence.
Yo, 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 yo.
So now it takes the exact same time for 6 sounds to play than for 18 sounds. And in another condition, we tested whether for newborns it was enough to have the temporal dimension and not having numerical cues. So now we are presenting 2 sounds, which are just separated by a variable interval of time, but there is no number because there's always 2 sounds. And this is how they look like, a short sequence.
Yo. Do. Na.
And this is a long sequence.
Yo. Yo.
It's 3 times the short sequence.
2. 2.
Okay. So here is the data that I showed to you before, where here is plotted the look-in time. This is the look-in time to the congruent mapping, to the incongruent mapping, in the condition when both numerical and temporal cues were available for the newborn to map onto a spatial length. Here is the condition when only number is available. Again, we replicate the preference. And here is the condition where only temporal duration is available. And we find a significant main effect with no interaction. Okay, so I think that newborns are telling us that they might come with a predisposition to relate these dimensions. I agree with that these data are still compatible with an interpretation of the existence of a unique system of magnitude that is dealing with all these dimensions, or with different systems, but that we come from birth with a predisposition to relate the representations. We don't know this. So now we will move to the other side of the number space mapping, which is how numerosities can be associated to spatial positions. And this study was done with 7-month-olds. So here we present to them increasing number, but from left to right. So we present the shortest, the smallest numerosity on the left, it disappears, appears the middle number on the center, it disappears, appears the largest number on the right. And we do this, the same thing, always left to right, for another group in which they are habituated to decrease in number. At test, we show them new numerosities, always left to right oriented, of both increasing and decreasing number. And this is the look-in times of infants during the test trials. When there is an interaction, as you can see, and when they are habituated to the increasing sequence, they look longer, significantly longer, to the familiar test trials, such as the trials which are new in numerosity but have the same ordering, always left to right, increasing left to right. And for infants that were habituated to decrease in number, there is a preference for the novelty. So they look also for increasing left to right oriented. We ran another experiment in which we used exact same methods. The only difference is that now we present the numerical information from right to left. So now the smallest number is on the right side, middle number on the center, and largest number on the left side. We do exactly the same. Another group is habituated to right to left oriented decreasing number. And at test, again, we presented new instances of numerosities, always right to left oriented, for both increasing and decreasing. And here we find that in neither of the two conditions, infants show evidence of having discriminated the ordinal direction. So I think that these data, at least these ones, are consistent with the idea that there might be a baseline preference for an increase in left to right oriented sequences. This is what we tested next. And in this experiment, we are just measuring baseline preference. So we are not habituating infants to anything. We are just showing to them a series of trials and just measuring the look-in time towards them. And the infants receive 2 blocks of trials, one in which there is increasing number, another there is decreasing number, but it's always left to right oriented. And it's, as I showed to you before, first one numerosity appears, then it disappears, appears the next one, it disappears, appears the next one. They receive 3 trials here, 3 trials here, and we just measure look-in times. Of course, we counterbalance which one starts with which. And what we found is that when we present to infants the increasing block first, they show a significant preference, significant higher look-in time for the increase in order relative to the decrease in order. And this preference might not be explained by an order effect, such that infants, we know that they tend to look more time to the first trials and their attention decreases, because in the group that started with the decrease in number, they didn't show this preference for the first trials. So there must be something more. And then we asked, maybe they have a preference, they prefer to see the information left to right oriented versus right to left oriented. The infant, they just prefer to see that something is appearing here, and then here, as opposed to the reverse. And here, again, is a baseline preference, so we don't habituate them to anything. We just present them a series of trials. Here's Donald Duck, because we wanted to get rid of the numerical information to see if this could extend to other information, or not ordinal or magnitude-related information. So we present a block in which Donald Duck appears on the left, then right, then center, then right, another block in which appears first on the right, then on the center, then on the left. But here, infants, they don't show any preference. They look equally to both orientations, no matter with which block of trials they started. So honestly, I was expecting that they would have shown a left to right preference that then is applied to any ordinal information, but we didn't find this. And I think that it might be that this Donald Duck has no ordinal meaning, actually. They didn't have the time to really learn the sequence and to have the ordinal information and to try to spatialize it, sorry. We are now testing this and trying to teach infants with statistical learning rules, so that we don't want to use size or number, which are magnitude related. We just want them to make them learn something that is ordinal and see if they prefer one orientation or the other. But this is work in progress, so we'll see. So now I hope I convinced you that infants, preverbal infants, show evidence of mapping numbers onto space in the same two ways as adults show it. And putting the pieces together, this is just throwing that an idea. I think that the origins of the mental number line might be found in early biases in the processing of number and of space. We have seen that there might be it might be inborn predisposition to relate these two dimensions, as we saw our newborns doing. We see that by 7 months of age, which infants already sit and grab things, they show a preference for increasing left to right oriented. And I think that we might find, so where does this orientation come from? It's true that still there might be some cultural effects, because these infants have had 7 months of life living in a world where the moms show the things from left to right in a world that is organized by us in that way. I don't know, but I think that ultimately we could find the origins of this left to right orientation. Well, this is in biologically determined biases towards the asymmetrical exploration of a space. And I think this bias might be applied with priority on increasing versus decreasing, because we found recently that at 4 months of age, infants are able to discriminate ordinal information, but just when it's increasing, not when it's decreasing. So there is an asymmetry in the emergence of ordinal information, and that's why I think that putting together all these things, we might have some kind of building blocks of a mental number line. Thank you.